Hello everyone, I am Shubhankar. In this video, I will be briefly presenting our work titled DOME Distributed Online Learning Based Multi-Estimate Fusion for Cooperative Predictive Target Tracking using a Robotic Swarm. As robotics technologies become more economical, miniaturized, and reliable, autonomous swarms are being increasingly considered for critical applications like search and rescue, precision drug delivery, surveillance, etc. In such applications, one of the fundamental tasks is cooperatively tracking a moving target. For search and rescue, it's mainly about tracking people. For precision drug delivery, it's about tracking cells. And for surveillance, it can be about tracking vehicles. A key challenge in cooperative target tracking with sensor equipped robots is the look ahead trajectory prediction. In heterogeneous swarms, where robots utilize varying sensors and diverse prediction algorithms, prediction accuracy among the robots can fluctuate wildly. Further, communication networks in real world environments can be unreliable as well. In such non stationary decentralized settings, the networked robots are required to find out whose prediction information should be trusted at what time. In this regard, the robotic swarm is required to exhibit a form of decentralized collective intelligence for decentralized adaptive fusion of shared predictions. This is where distributed online learning can help us induce such a collective intelligence in the swarm. Let us first describe the problem of cooperative predictive target tracking that we are dealing with. We consider a decentralized scenario where multiple robots are trying to predict the trajectory of an unknown target or bogey over a random communication network with a link drop probability of PLD. Each robot, indexed by I, runs a unique prediction algorithm AI that estimates the target's look ahead trajectory using only its onboard sensor suite SI. It is assumed that all the robots have access to the target's true current position. I will discuss more about this assumption's practical validity in the next slide. The tau step look ahead prediction generated by prediction algorithm AI can be expressed as an additive sum of the true target position after tau time steps and a drift term. The prediction drift is assumed to have an arbitrary unknown structure that may be non-Gaussian and lack a known distribution or be adversarial. This tau step look ahead prediction is then fed to a decentralized multi-estimate fusion block along with the prediction information from the neighboring robots to generate a socially fused prediction. This final output of fusion block is then used by the robot's control law to execute appropriate tracking maneuvers based on a specific robotic swarm application. In all this, our focus is the decentralized multi-estimate fusion block. We assumed that all the robots have access to the target's true current position. Such an assumption is highly viable in the real world under two operational paradigms. The first is the decentralized sensing and learning, where the robots, equipped with high-grade, long-range, wide FOV sensors, are capable of independently monitoring the target. But this can turn out to be very costly. The second is the centralized sensing and decentralized learning, where powerful centralized assets such as radar, satellite AWACS monitor the target globally and broadcast its current position to the robotic swarm via one-way communication. This paradigm enables cost-effective, scalable deployment of swarm systems. Now, let us discuss existing approaches to decentralized multi-estimate fusion that we have treated as baselines in the study. First, we consider four covariance-based methods that typically require covariance information and make assumptions regarding consistency and correlation. When a robot experiences severe dynamic bias that is not reflected in an inflated covariance estimate, these methods can fail catastrophically. Among these, the separate bias Kalman consensus fusion is the most robust, which assumes that the bias or the drift follows a random walk process. While this allows it to explicitly extrapolate feature drift, its rigid internal physics model breaks down completely when faced with arbitrary or non-stationary switching bias. We also consider the averaging consensus fusion as a baseline, which assumes equal weights for all the predictions or estimates in the consensus fusion process and does not require covariance information. However, ACF is not adaptive. Further, we consider two online learning methods, distributed mirror descent and greedy local, that also do not require covariance information. DMD assigns equal weights in the consensus layer, but involves an online error correction mechanism. Assigning equal weights in the consensus fusion layer allows adversarial or highly biased predictions or estimates to propagate unchecked through the network, poisoning the entire swarm. Greedy local, however, does not involve any consensus process, but instead does a greedy selection of the most accurate prediction or estimate based on a cumulative loss score. The DOME fusion algorithm consists of four phases in a feedback loop. In the learning phase, the current target position is accessed, which is used to calculate the prediction losses. Using a multiplicative exponential weight strategy, the hat weights are updated using the prediction loss calculations based on the associated previous time step predictions. Further, a periodic reset mechanism ensures that the hat weights are reset to 1 after every t0 discrete time steps. Next, these alpha hat weights are utilized in the local fusion phase to get the local trust weight, which is used to generate the local prediction by fusing the local algorithm's prediction with its previous time step social prediction. In the communication phase, robots share their local predictions and their W hat weights with their neighboring robots as per the communication network. Next is the social fusion phase, which utilizes the communicated W hat weights to generate social trust weights that are further used to get social prediction by fusing the shared local predictions. The social prediction is fed back to the learning phase and the local fusion phase in the next time step and is also used by the control law. For DOME's theoretical analysis, we consider two reasonable assumptions. The first assumption ensures that within any given neighbor set, a unique optimal predictor exists asymptotically. And the second one ensures that the cumulative loss difference between other robots and the best performing robot grows at least sublinearly with time. Under these assumptions, the theoretical analysis establishes that the expected values of the social fusion weights converge over time. More specifically, the expected values of the weights assigned to the robots with inaccurate local predictions converge precisely to zero, whereas those assigned to the robots with the most accurate predictions converge to a finite value dependent on the communication link drop probability. This theorem guarantees that within any stationary epoch between periodic resets, the DOME algorithm will mathematically filter out adversarial or drifting nodes, adaptively routing trust through the unpredictable network topology. DOME's performance is evaluated extensively using a MATLAB simulation. With a time horizon of 1400 time steps, a sampling period of 0.1 second, and a look ahead window of 10 time steps, DOME is implemented on a swarm of 6 robots communicating over a random network with an underlying undirected connected linear topology. Further, the link drop probability is set to 10%. For this simulation, the drift model is assumed to consist of two additive terms. The first is a bias term and the second is a zero mean Gaussian noise term. The bias term is assumed to follow a stochastic switching bias model as shown. At certain time instants, robots are randomly assigned either CTI equal to 0.01 or CTI equal to 4, such that approximately 50% of the total robots have inaccurate prediction algorithms, that is, for them, CTI is equal to 4. Along with the high inaccuracy induced randomly at different times, which injects massive spatial errors that are up to 40 meters. Such a switching bias model is chosen to stress test DOME against uncertainties associated with sudden sensor occlusions, algorithmic failures, or abrupt target maneuvers in real-world operations. Further, the random communication network also adds on to the adverse situation that the swarm has to go through. Note that DOME was not provided any information regarding the drift model and the communication link drop probability. Around 500 simulation runs were carried out, each with a unique random seed, to evaluate DOME and the baselines. DOME was evaluated against the baselines based on the average cumulative tau step look-ahead prediction loss. The results revealed that DOME performed the best, showing approximately 74% loss reduction compared to the next best method, SBKCF. Here is a video of a simulation run. The bottom middle plot shows which robot's algorithm goes bad at what time. The bottom right plot shows the communication link drops happening in real time, along with which robots or nodes are entering the growing bias state. Check the top right plot along with the bottom ones to observe how DOME performs when sudden switches happen. This simulation video is 1 minute 10 seconds long, so you may skip it to proceed to the next slide. Further, we also conducted a scalability study. The results show that as we incrementally add robots to the swarm, maintaining a linear network topology as before, the dome maintains a minimum 72% reduction in prediction loss relative to the baselines. Beyond 10 robots, dome's performance curve essentially flattens, indicating that the algorithm scales well without compromising predictive accuracy. The ablation studies further revealed that while the social fusion layer has the greatest overall impact on performance, the adaptive weighting is actually more critical in the local fusion layer, acting as a vital quarantine zone against internal sensor failure. The periodic reset mechanism, however, is a critical component as it forces the swarm to routinely discard historical bias and re-evaluate the network based strictly on recent performance. Dome proved highly robust to network degradation, maintaining acceptable prediction loss even when the probability of communication link drops reached 50%. Building upon the availability of ground truth observations, we must also consider their imperfections. To do so, we consider the second paradigm of centralized sensing and decentralized learning, where a centralized asset broadcasts noisy observed target positions to the swarm. Here, the noisy observations consist of a constant magnitude noise with randomly changing direction. The results show that DOME is highly resilient to observation noise. Even when injected with noise up to 10 meters in magnitude, the average cumulative prediction loss increases by less than 83%, remaining well within acceptable tracking tolerances. This makes DOME highly compatible with modern LiDAR inertial odometry or the centralized radar or satellite broadcasts we discussed before. While the MATLAB simulations utilized holonomic kinematics, DOME is fundamentally model agnostic. To show this, we successfully implemented the dome fusion algorithm to non-holonomic kinematics in a ROS Gazebo physics simulation. This simulation video is 1 minute 43 seconds long, so you may skip it to proceed to the concluding slide. In conclusion, DOME is a distributed online learning based multi-estimate fusion algorithm that involves weighted fusion of local and social predictions, where the weights adapt via a loss-driven online learning mechanism to handle unknown, arbitrarily structured prediction bias and random communication link drops. Theoretically, it is proven that the conditional expectations of the fusion weights converge. The simulation results show that DOME outperforms baselines, achieving 74% lower prediction loss compared to them. Further simulation studies revealed that DOME is scalable and resilient to network degradation and noisy observations. While designed for robotic swarm operations, the underlying mathematics of DOME can generalize to any decentralized, privacy-preserving prediction task. The DOME framework holds immense potential for cooperatively predicting trends in financial markets, integrating heterogeneous models in weather forecasting, jointly improving predictive diagnostics without sharing sensitive healthcare data, or cooperatively predicting energy availability and demand under uncertainty.